This lecture introduces linear second-order ODEs on a fixed interval, emphasizing solutions, boundary conditions, and eigenvalue problems. We develop the concept of linear independence via the Wronskian, show why only two independent solutions exist, and use the Wronskian to construct a second solution. When we talk about functions being linearly independent, we mean that no function in the set can be written as a constant combination of the others. Let y1 of x through yk of x be functions on an interval I. Formally, if the only way that d1y1 plus d2y2 plus dkyk equals 0 for every x in the interval I is by setting all the constants d1 through dk to 0, then the functions are independent. Otherwise, they're linearly dependent. But the interval really matters. Take y1 equals x cubed, and y2 equals the absolute value of x cubed. On the whole real line, these two behave differently and are independent. Yet on the interval from 0 to infinity, they coincide. So one is a multiple of the other, and the pair becomes dependent. So independence isn't just about the functions themselves, it's about where you compare them. When we have several functions, y1 through yk, each differentiable enough times, we can test whether they are linearly independent by looking at all their derivatives. We start from the defining equation d1y1 plus d2y2 plus dkyk equals 0, and then take its first, second, and so on, up to the k-1 derivative. That gives us a whole system of equations, one for each derivative order. We can then arrange these into a matrix, whose first row contains the functions, the second row their first derivatives, and the last row their k-1 derivatives. This matrix is called the Wronskian matrix, and multiplying it by the column of constants d1 through dk must give the 0 vector. The determinant of that matrix is the Wronskian, written w of x. If this determinant is not equal to 0, at least at one point, say x0, then the matrix is invertible there, and the only possible solution to the system is that all the constants d1 through dk vanish. That means the functions y1 through yk are linearly independent at that point. To guarantee independence throughout the interval, the Wronskian must stay non-zero for every x in the interval I. Now, it's important to realize that the converse of our Wronskian test does not hold. If the Wronskian w of x equals 0 for every x in the interval, we cannot automatically conclude that the functions are linearly dependent. For example, take y1 of x equals x cubed, and y2 of x equals the absolute value of x cubed. If you compute the Wronskian, you find it is identically 0 for all real x. Yet, these two functions are actually independent on the whole real line because one cannot be written as a constant multiple of the other when x is negative. However, on the half-line from 0 to infinity, they become dependent since x cubed minus absolute value of x cubed equals 0 for all x greater than or equal to 0. So remember, a vanishing Wronskian is a necessary but not sufficient condition for dependence. To see a clear independent case, let's take y1 equals cosine of x and y2 equals sine of x, defined on the interval from minus pi to pi. The Wronskian determinant here is cosine squared x plus sine squared x equals 1, which is never 0. This confirms that sine and cosine are linearly independent, not just on this interval, but everywhere on the real line. Consider a normal second-order homogeneous linear differential equation, a2 of xy double prime plus a1 of xy prime plus a0 of xy equals 0, where a2 of x is never 0 on the interval I. The theorem says, two solutions, y1 and y2, are linearly independent if and only if their Wronskian w of x equals y1 times y2 prime minus y1 prime times y2 never vanishes on that interval. The assumption of normality guarantees that the initial value problem has a unique solution for any given data, a fact we'll use in the proof. Suppose the Wronskian is non-zero at some point, say x star. Then the 2x2 matrix made of y1, y2, and their derivatives at x star is invertible. This means the only constants d1 and d2 that make both d1y1 plus d2y2 equals 0 and d1y1 prime plus d2y2 prime equals 0 are the trivial ones, both 0. Therefore, no non-trivial linear combination of y1 and y2 can vanish at the point x star with derivative 0 there. By the uniqueness theorem for the initial value problem, the only solution that satisfies both y equals 0 and y prime equals 0 at that point is the trivial one, the 0 function. Hence, y1 and y2 are linearly independent. Conversely, if y1 and y2 are linearly independent, then their Wronskian can never vanish anywhere on the interval. For suppose it does vanish at some point x0. Then the linear system built from the values and derivatives of y1 and y2 would have a non-zero solution for d1 and d2, meaning the linear combination d1y1 plus d2y2 satisfies y equals 0 and y prime equals 0 at that point. But the initial value problem with data y of x0 equals 0 and y prime of x0 equals 0 has a unique solution, y identically 0 on the interval I. Therefore, d1y1 plus d2y2 is identically 0 on I with d1, d2 not both 0. That is, y1 and y2 are linearly dependent. In short, for two solutions of a second-order homogeneous linear ODE, the Wronskian provides a perfect test. If it never vanishes on I, the solutions are independent. If it vanishes at any point, the solutions are dependent. The Wronskian, therefore, captures the entire structure of independence in this case. Consider again a normal second-order, homogeneous linear differential equation on the interval I. Another important theorem states that there can be at most two linearly independent solutions on such an interval. To prove this, suppose we have three solutions, y1, y2, and y3. We form their Wronskian, the determinant of the 3x3 matrix built from the functions, their first derivatives, and their second derivatives. Next, we use the differential equation itself to replace each y double prime sub j by minus a1 over a2 times y prime sub j minus a0 over a2 times y sub j. When we substitute these expressions into the last row of the determinant and then perform the standard row operations, which do not change the value of the determinant, the third row becomes all zeros. This means the Wronskian w of x is identically 0 everywhere on the interval. So, at any point x0, the functions satisfy a non-trivial linear relation. There exist constants d1, d2, and d3, not all 0, such that both d1y1 plus d2y2 plus d3y3 equals 0, and d1y1 prime plus d2y2 prime plus d3y3 prime equals 0. Let y of x be that combination. Then y of x0 equals 0 and y prime of x0 equals 0. By the uniqueness of the initial value problem for a normal homogeneous equation, the only such solution is the trivial one, y identically 0. Hence, the three functions are linearly dependent, and any second-order homogeneous ODE can have at most two independent solutions. We state now a central result. If y1 and y2 are two linearly independent solutions of a second-order, linear homogeneous ODE, then every solution can be written as a linear combination, y of x equals a times y1 of x plus b times y2 of x, with a and b constants. So y1 and y2 form a basis for the solution space. Once we know these two, we know them all. In fact, the Wronskian provides a way to construct one of these two basis solutions directly from the other. Let y1 and y2 be solutions and define the Wronskian w of x equals y1 times y2 prime minus y1 prime times y2. We differentiate w and use the differential equation for both solutions to obtain w prime equals minus a1 over a2 times w. This first-order equation integrates to give an explicit form of the Wronskian given in equation 25. Assume y1 is known and non-zero on some subinterval. Write y2 equals v times y1. Then the Wronskian becomes w equals y1 squared times v prime, which is y1 squared times the derivative of y2 over y1. Equate this to the explicit w of x we just found and integrate. We then get y2 of x in terms of y1 of x, as in equation 26. In summary, the Wronskian reveals the structure of all second-order linear ODEs. Two independent solutions form a complete basis, and once one is known, the other, and every solution follows.